Welcome to Chapter 3, Subskills. In this video, we are going to look at the domain and operations on rational expressions, and we will also simplify complex rational expressions. We will evaluate functions given either an equation or the graph, and we will determine if a relation is a function from the graph. And lastly, we will look at the graphs and equations of circles. So let's look at example 1. Find the domain of the rational expression. The first rational expression is x plus 2 all divided by the quantity x minus 3. One thing we want to remember is that if we have 0 divided by a number, that just simply equals 0. So for example, 0 divided by 11 is just 0. However, if we have the 0 in the denominator or 11 divided by 0, then this expression is undefined. So essentially, when we're trying to find the domain of a rational expression, we're trying to make sure that the denominator does not equal 0. So in this situation, the x plus 2 is not risky for us. The only thing we have to focus on is the denominator x minus 3. And we just want to make sure that x minus 3 does not equal 0. So it could be anything except x minus 3 cannot be 0. So to solve this, we will add 3 to both sides, just like we would do if it were an irregular equation. And we get that x cannot equal 3. So in set builder notation, we could write that as all x values such that x does not equal 3. Now, if we also wanted to include interval notation, let's think about that. We have all numbers on the number line except for 3. So in essence, we have to the left of 3 and to the right of 3, it's just not equal to 3. And so we end up having 2 intervals here. One on the left will go from -infinity to 3 using a parenthesis so that we do not include the 3. And then we'll pick up again and again go from 3 to infinity. And notice parentheses on both of the intervals because we want to make sure that 3 is not included. Okay, so our domain of the expression x plus 2 divided by the quantity x minus 3 is x cannot equal 3, or in interval notation, it's -infinity to 3 union 3 to infinity. Now let's look at the next expression. We have 10 divided by 4x squared. Again, if we're looking to find the domain, all we need to do is ensure that the denominator does not equal 0. So 4x squared cannot equal 0. Now, we could go ahead and solve by dividing by 4 and such, but we could also observe that the only way that 4x squared will equal 0 is if x equals 0. So we could just reason through that x cannot be 0, or I'll show the algebra. Let's divide both sides by 4. So x squared cannot equal 0. And we could use that square root property or take the square root of both sides. We don't need a plus or minus because it's 0, and we get x cannot equal 0. So again, we can write this in set builder notation. We do curly brackets with the X, a vertical line, and then the expression X cannot equal 0. And that is read all real numbers X such that X does not equal 0. And if we wanted to also include interval notation, just as we had before, we're going to get those two intervals, negative infinity to 0, union 0 to infinity, all parentheses, no brackets. Okay, so notice in this situation, we were not necessarily simplifying these expressions. All we were asked to do was to find the domain. So now we're going to move on to some operations on rational expressions, and we will start with multiplying rational expressions. I just noticed I'll label this A and B instead of C and D. Okay, so if we're going to multiply 2x over 3 times 180, we need to recall the rules for multiplying regular fractions. So if I have one fraction times another fraction, like A over B times C over D, first of all, I can reduce any of the quantities in the numerator with any of the quantities in the denominator if possible. And then if not, we just multiply straight across. So we'll get A times C is AC, B times D is BD. Again, when it is multiplication of two rational expressions, at this stage, we may reduce first. So let's go right ahead. We have 2x divided by 3 times 180. So I can rewrite 180 as a fraction and write that as 180 over 1. Anytime we need a whole number as a fraction, we can put it over 1. And I have a choice. I can either multiply straight across first and then divide, or we can reduce first and then multiply across. So I'll show both in this example. So here, if we just multiplied straight across, we'd get 2x times 180, or 360x divided by 3. And now we can divide 360x by 3 to get 120x. So we can see that is definitely an option. However, we want to move in the direction instead of trying to get in the habit of reducing first. So notice that the 3 in the denominator can reduce with the 180 in the numerator. And again, anything in the numerator can reduce with anything in the denominator when it's all multiplying and it's two fractions. So since 3 goes into both 3 and 180, we can divide each of those by 3. So 3 divided by 3 is 1. 180 divided by 3 is 60. And remember the trick, you can just do 18 divided by 3 is 6. So 180 divided by 3 is 60. Just kind of let that 0 tag along. And now I'm ready to multiply straight across. So we can now multiply 2x times 60 is 120x, and 1 times 1 gives us a denominator of 1, or 120x. So notice in this case, in this situation, it didn't matter if we multiplied straight across and then divided, or reduce first and then multiply straight across. I will, from now on, I'm going to mostly do this method where we reduce first, because when our expressions get more complicated, it's very important to make those quantities smaller before we make them bigger and more complicated. So now let's go ahead for part B. 12x over 15y to the fourth times 10y cubed over 4x to the fifth power. I will take this one step at a time. First, I'm going to reduce the numbers. So notice that 12 and 4 can both be reduced by 4. So I will divide each of them by 4. 12 divided by 4 is 3, and 4 divided by 4 is 1. In addition, we can see that 15 and 10 can both be divided by 5 evenly. So I will divide them both by 5. 10 divided by 5 is 2, and 15 divided by 5 is 3. So, of course, we can do more simplifying here, but just to keep it organized, I will go ahead and just write out what we have so far. So we have 3x over 3y to the fourth times 2y to the third over x to the fifth power. So now we can actually reduce the numbers even more. The 3's are both divisible by 3, so we'll divide them both by 3 and get 1. And now we're ready to simplify our x's. So we have x to the first power on the top and x to the fifth power on the bottom in that denominator. So the exponents, or we will subtract the exponents, 5 take away 1, and we get 4. But notice now we will be left with x to the fourth power in the denominator, since there were more x's in the denominator than in the numerator. In addition, we have y to the fourth in the denominator and y to the third power in the numerator. So 3 of those y's will cancel out and we'll be left with 1 y. Again, there are more y's in the denominator, so we will be left with 1 y, or y to the first power, in the denominator. And so and then the only thing that's left up top is the 2, because the x canceled out on the top and the y cubed canceled out on the top. And so our final answer is 2 over x to the fourth power y. And that is now our simplified answer, because each base, x, y, and 2, only appear once. Next, we will move on to dividing rational expressions. Again, let's quickly review the rules for dividing fractions. So if we have, in this case, a over b divided by c over d, the first move will be to multiply by the reciprocal of c over d. So a over b stays the same. That first fraction will stay the same, but we will multiply by the reciprocal of the second fraction. So we will flip c over d to get d over c. Again, if we can, we will reduce first. If not, or it's an option to always then multiply straight across. So now we'll get AD over BC. So let's put this into action now. So here if you prefer to rewrite this division, we could rewrite this as 42x divided by 6y over 7x. Again, we will write the quantity 42x as a fraction by putting it over 1. And so now we keep the 42x over 1, but we will flip the quantity after the division symbol to get 7x over 6y. Always feel free to go from this original problem and just flip the denominator and multiply. So that's another option, is to skip that initial step. However, I find that it's nice to kind of write things in a more familiar way whenever we're in doubt. So here we go. Let's reduce first. We can reduce both 42 and 6 by 6. So 6 divided by 6 is 1. 42 divided by 6 is 7. And now we're ready to multiply straight across. 7 times 7, 49. X times x, x squared. And 1 times y is y. And we are now done since each base appears once. Okay, now for B. And this is a great time where you may try and pause, try this next one on your own, see how it goes. So let's take a look. Again, if I'd like, I can rewrite this division using the traditional division symbol with fractions. 14x over 20y divided by 21x over 30y squared. And now I'm ready to flip the quantity after the division symbol and multiply. So 14x over 20y stays the same, but now I'm going to multiply by 30y squared over 21x. Let's first reduce the numbers. So we might see that 20 and 30 can both be divided by 10. So 20 divided by 10 is 2, 30 divided by 10 is 3. And also 14 and 21 can both be divided by 7. So 14 divided by 7 is 2, and 21 divided by 7 is 3. And now we can see that the 2's can both be divided by 2, so the 2's cancel out, as well as the 3's. So now I will go ahead and just write what we have so far. On the top, we have xy squared, and on the bottom, we have just an xy. So we have the x and the y and nothing else. So now we have the x's cancel out entirely. And then the y's, one of the y's will cancel out, and we are only left with y to the first power on top. We'll leave 1 as a placeholder on the bottom, but that just equals y. So that whole expression that we started with actually can be simplified down to y. Okay, now we're going to get into adding rational expressions. So remember, when we have two fractions to add, we need common denominators. So let's look at something like 1/4 plus 2/3. So we need something where both 4 goes into a number and 3 goes into that same number. So we're option for this is you can kind of think, okay, we can count by fours. 4, but 3 doesn't go into 4. Then 8, 3 doesn't go into 8. 4, 8, 12. Aha. 3 and 4 both go into 12. So that is the denominator I am going to go after. So, and then, well, how do I change 1/4 into 12ths? Well, I can multiply the top and the bottom by the same exact quantity. So I think 4 goes into 12 3 times. So I can multiply the top and bottom of this fraction by the same amount. And so we get 1 times 3 is 3. And notice if we reduced 3/12, we don't want to, but if we reduced that 3/12, we get back to the 1/4, showing that equality. Same thing, we'll go 3 goes into 12 4 times, so we'll multiply top and bottom by 4, and we get that 8/12. Again, if you were to reduce that 8/12, we get back to the 2/3 so you can see that equality. And then we multiply, or we're ready now to add those two fractions, and we add the numerators. 3 plus 8 is 11, but the denominator stays the same. And remember, this is the 12 tells us the size of the piece. So we have 3 of these pieces plus 8 more of these pieces. So we have 11 of these pieces, and these pieces are 12ths. So let's go ahead now on part A. 3x divided by 7z plus 5 over 4z. So we need a common denominator. So that's kind of a big key. We need a common denominator. So let's see what we get. All right. So I can count by my, or I like to kind of treat the 7 separate from the z. So first, let's decide that 7, 4 doesn't go into 7. 14, nope. 21, no. 28, yes. 7 and 4 both go into 28 evenly. And since they both just have a z, just a z, the denominator will be 28z. If they had different variables, we'd need one of each variable. Now we need to find how to convert this 3x over 7z into a fraction with a denominator 28z. So we're asking 7 times what gives us that 28z? So 7z times what gives us that 28z? And it's 4. So we're going to multiply top and bottom by 4, or we'll multiply the numerator by 4 and the denominator by 4. 4 times 3x gives us 12x in the numerator. Now we're ready to do the same on the right. We're trying to get 5 over 4z to be written as a denominator of 28z. So we're thinking, 4z times what gives us that 28z? And in this case, it's 7. So whatever we do to the bottom, whatever we multiply by the bottom, we have to multiply the exact same quantity to the top. And 5 times 7 gives us 35. And now we're ready. Just like when we're doing fractions up above, the 12, the denominator stayed the same. Same thing with rational expressions. When we add fractions, we find a common denominator, and then the denominator needs to stay the same, 28z. And then we will add the numerators. However, notice that 12x has an x, but the 35 does not. So we will just write that as 20 or 12x plus 35. All right, so that is our final answer now. The 12x plus 35 all over 28z. And notice that even though the 35 and the 28 normally could be reduced by 7, in this case, we cannot reduce those because the top, the numerator, has addition in it, and we cannot cancel addition over division. So that is our final simplified answer. So now we're ready. We have 3x squared over 10 minus 2x over 5 plus 5x squared over 2. So now we need to find the least common denominator between 10, 5, and 2. So if we look at the biggest denominator there, 10, notice that 5 goes into 10 and 2 goes into 10. So our least common denominator of 10, 5, and 2 is 10. So now we're trying to write every single one of those fractions with a denominator of 10. Now the first fraction already has a denominator of 10, so we will just leave that as 3x squared over 10. The middle fraction, we're trying to change that fraction's look, but still keep the value the same. And so we have to figure out 5 goes into 10 how many times? 2. So now we'll multiply the top and bottom of that rational expression by 2. And we get 2x times 2 is 4x. On the right, we're trying to figure out what we need to do, what we need to multiply 2 by to get 10. So we'll multiply by 5 since 2 times 5 is 10, and we'll multiply top and bottom by 5. 5x squared times 5 is 25x squared. And now we're ready. We have common denominators, so we're ready to add and subtract these quantities. The denominator stays the same. And then notice we can add 3x squared to that 25x squared. So we get 28x squared. And the minus 4x cannot be combined since those other two terms have x squareds and the 4x only has an x. So those are not like terms. So now we notice that 28, 4, and 10 can all be reduced by 2. So the shortcut would be, okay, as long as every single quantity can be reduced by the same number, we could do that. So we'll divide all of these 3 quantities by 2 to get, so 28 divided by 2 is 14, 4 divided by 2 is 2, and 10 divided by 2 is 5. And so I'll put that off to the side. So we should get 14x squared minus 2x all over 5. All right, so that's one option to do it that way. However, that's kind of more of a shortcut and not being very careful. So I'll show you why that's allowed. So if we notice that they can all be divisible by 2, then we can decide to factor a 2 out of the numerator. And what I mean by that, it's kind of like the reverse of the distributive property. So since 2 goes into 28 and 4x, I can now write this, pull the 2 out, and then I'm left, I can then go 28 divided by 2 is 14x squared. And I also have to pull the 2 out of the 4. 4x divided by 2 is 2x. And leave the 10 on the bottom. And now take a look. If I distributed this 2x back, I'd get 28x squared. That's right. And then I'd also get minus 4x. So these are in fact equivalent. However, now that we have multiplication over division, now we can go ahead and cancel the 2 and the 10, reduce them both by 2. So 2 divided by 2 is 1, and 10 divided by 2 is 5. And there we will get our final answer of 14x squared minus 2x all over 5. And notice that was the same as our shortcut that we did as well. So it's up to you. This method here is really being very careful algebraically. However, if you know when you can use that trick, you're welcome to do that as well. All right. So that is all we're going to do for now on our operations on rational expressions. We will again, in chapter 4, we will then look at some factoring. And in chapter 5, we will again visit rational expressions that combines what we just did here with the factoring. Because trig has the algebra in trig is really intense when we get a lot of rational expressions or complex expressions. I wanted to make sure we really give our attention to these rational expressions. So let's go on to complex rational expressions, another algebraic piece that can come into trig. So there are a couple different methods that work well with complex rational expressions. Now, my favorite is to find the LCD of all of the denominators. So I'll go ahead and focus on that method here. So what I need to do first to do this method is I need to find the LCD of 7 of all of the inner denominators. So 7, 4, 2, and 14. So let's find the common denominator with all 4 of those numbers. So again, I like to count by that biggest number. So 14, 7 goes into 14, but 4 does not. So I'll keep going. 14, 28. I'm just counting by the largest number. 7 goes into 28, 4 goes into 28, 2 goes into 28, and 14 goes into 28. So the LCD of all of those numbers is 28. So one option is to go ahead and multiply the top and the bottom by the LCD. So I could just multiply the top and the bottom by 28. And this is allowed because I'm just multiplying the top and the bottom of that overall fraction by the same number. So I'll go ahead and we will now need to distribute that 28 to both terms in the numerator and both terms in the denominator. So first I'll just copy the original problem. And then I'll multiply each term by 28 over 1, since I can write 28, the whole number 28, as a fraction with 28 over 1. And now we're ready. So on the top left, I'm going to go ahead and reduce first. So I'm going to reduce the 7 and the 28. Both of those can be divisible by 7. So divide by 7, 1. 28 divided by 7 is 4. And now I can multiply the 4 times 3x and get just 12x over 1, or just 12x. Top right. Notice 4 and 28 can both be divided by 4. So I will divide those both by 4 and get 1 and 7. And now I'm ready. 5 times 7 is 35 over 1, which is just 35. Bottom left will reduce by 2 to get 14x. Bottom right will reduce by 14. So 14 divided by 14 is 1. 28 divided by 14 is 2. And now we multiply. 9 times 2 is 18 over 1. So we get minus 18. And there we have it. Since 12 and 35 don't have anything in common, we can't factor anything out there. So nothing could cancel with the bottom. And notice here, the 12, the 14, and the 18 can all be reduced by 2. However, since 35 cannot be reduced by 2, this expression is simplified. So our final answer is 12x plus 35, all divided by 14x minus 18. Now, for some of you, that method is a little unsettling. And so if that's the case, I will show you another method. There's actually multiple methods, but another one that I've really liked is I'm going to copy down the original problem. Now, what we will do is we'll just find a common denominator on the top and find a common denominator on the bottom. So with 7 and 4, the common denominator will be 28. And so on the top left, I'll multiply top and bottom by 4. Top right, I'll multiply top and bottom by 7. So I get 12x over 28 plus 35 over 28. And then I'll do the same on the bottom. So I get the common denominator between 2 and 14 is 14. On the bottom left, we multiply top and bottom by 7. On the bottom right, we already have our fraction in terms of 14, so we just get 9/14. And now we can go ahead and write that as one fraction on the top, 12x plus 35 all over 28, and then one fraction on the bottom, 7x minus 9 all over 14. And now that we have one fraction over another fraction, we can flip the bottom and multiply. So that 12x plus 35 over 28 will multiply by 14 over 7x minus 9. And now we can reduce 28 and 14 by 14. So we will get 14 divided by 14 is 1, 28 divided by 14 is 2. So now we're ready to multiply straight across, and we get the 12x plus 35 in the numerator, and then 2 times the parentheses, 7x minus 9 in the denominator. And notice it would be equivalent to the expression we found before, or we could just leave it factored. So normally your answers, you would multiply anything out, like the 2 outside the parentheses. However, there's a common agreement that because rational expressions, we often will be factoring things out. It's convenient to have things in factored form. So you may leave your answer factored or you can multiply it out. So either of these two answers would be acceptable, but you can see that they're equivalent. Okay, now we're ready for B. And on this one, I'm just going to go with the original method of finding that LCD. So first, what's the LCD of 10, 5, 2, and 10? And as we saw before, that common denominator is 10, since 5 and 2 both go into 10. So now I'm going to go ahead and multiply top and bottom by 10. And that's allowed because I can multiply top and bottom of that big overall fraction by 10. So I'll copy down the fraction. Or all of the fractions. And these are called either complex rational expressions or complex fractions. And now I'll multiply each of those quantities by 10 over 1 because we need to distribute the 10 to all of those terms. Top left, the 10s cancel out, and we're just left with 3x squared. Top right, we can reduce 5 and 10 by 5 to get 1 and 2. Then we multiply 2x times 2 to get 4x. Bottom left, we can reduce 10 and 2 by 2 to get 1 and 5. And then we multiply straight across and we get 5x squared. Again, it's over 1, so we just get 5x squared. And on the bottom right, the 10s cancel. And we're just left with minus 3x. So we have 3x squared minus 4x all over 5x squared minus 3x. In this situation, we see that every single one of these terms in both the numerator and the denominator all have x's in them. So what we're going to do is we're going to factor out an x. So since the top two terms both have an x in common, we can factor out the x, and we're left with 3x minus 4. In the denominator, we have an x in both of those terms, so we'll factor out the x, and we're left with 5x minus 3. Again, you can always multiply back that x to check that they are equivalent. And now those x's will just cancel right out, because x divided by x is just 1, and we get our final answer, which is 3x minus 4 all over 5x minus 3. And that is our final answer. And again, we cannot cancel out those 3's at all because there's adding or subtracting over division. Okay, we're going to switch gears now, and we're going to look at function notation. So we're going to explore functions in different capacities. But first, we want to look at this notation. So first of all, for part A, we're going to evaluate this f of 2. So notice the language, f of negative 2. So this is function notation, and they're telling us the function f of x equals negative x squared plus 4. So we're now trying to find f of negative 2. And so basically, if you look, what's inside the parentheses in the formula, that's x. So now we have a -2 inside the parentheses. So we're going to plug in that -2 into x into the formula. So we're going to plug in that -2 in for x. So we get negative of -2 squared plus 4. So we have to be careful with that double negative. Technically speaking, this negative out front could be seen as multiplying by a -1. And I'm going to just write it that way, just so we can see that this is really an order of operations issue. We have to do powers first. So we will find that -2 squared, which is -2 times -2, or a +4. But then we will multiply that by the -1. So then we end up getting -4 plus 4 equals 0. So if you do not write this out, it's more than acceptable to go straight from the negative of -2 squared plus 4. But what I like to think of is anytime you put a real number into negative x squared, you're either going to get a negative or 0. So you can just see that and go, oh, okay, I'm going to take the negative of -2 squared. You get a +4 and drop down the negative. So this notation, f of -2 equals 0. What this says is that my function equals 0 when x equals 2. And on a lot of times up till now, before you see function notation, when we have equations, we would have x and y. So this formula would be comparable to y equals -x squared plus 4. And so this right here, when we find our functional values, it's like finding our y values. So that would also give us the point -2, 0 on the graph if we were to plot this on an xy plane. And then last but not least, this f of -2 does not mean f times -2. It means that the functional value equals 0 when x equals -2. So let's go on to the next one. G of 0, we're to find g of 0 when g of x equals 2 cosine x. Okay, so now we're applying it to our trig functions. So g of 0 equals 2 cosine, and now I'll put the 0 in for x, so cosine 0. So we have 2 cosine 0. So now we need to figure out what is cosine 0. Well, when my angle is 0, then what are the values there? Well, I can pick an xy coordinate and say, okay, well, I could pick 1, 0, then r equals 1. So cosine of 0 is x over r, or 1 over 1, which gives me 1. So now I can substitute my cosine of 0 with 1, and I will multiply 2 times 1 is 2. So I just found g of 0 equals 2. And that's my final answer. Now for part C, we are not given an equation. Instead, we are given a graph, h of x. So we're going to use the function notation and see how it applies to the graph. So the first one, h of 0. Let's take a look at that. So this is h of 0 is telling me to find y. So kind of what that means right there is to find y when x equals 0. Okay. So x equals 0 means I don't go side to side at all. I'm just at the origin and I'll go up and down. So let's look for the graph. And there it is. And what is the y value there? Y is -2. So h of 0 equals -2. Let's try the next one. Now, h of pi is telling us x equals pi. What is y? So let's now go over to x's pi, and notice our graph is right here on that x-axis. So I don't go up, I don't go down. And in fact, that coordinate is pi 0. So when x is pi, y is 0. So h of pi equals 0. And last but not least, we have h of x equals 2. This is different. This is inherently different. Now they're giving us h of x. So they're actually telling us that y is 2 and we need to find x. So now I'm going to go up to y equals 2 and look for my graph. And there we found it. Ding, 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 ding. And we found x is 2 pi. So my 3 answers for this one is h of 0 equals -2 because of that point 0, -2. H of 0 or h of pi equals 0 because of that point 0 pi, because of that point pi 0. And last but not least, we found that when h of x equals 2, x can equal 2 pi, and that's because of that point 2 pi comma 0. All right, next, let's move on to relations. So relations are just pairs of x and y coordinates, or a graph that relates two different coordinates, usually x or y. However, a function is a special relation where each input or x value corresponds to only one output or y value. And now let's decide if each relation is a function, and we will state the domain and range. So in order to determine if a relation is in fact a function, we will utilize the vertical line test. Okay. So a relation is a function if each vertical line passes through your graph at most once. So we'll go ahead and test it. Let's test with different vertical lines. So if I take this vertical line right here, or this one on this first graph, notice that every single vertical line will only cross that graph once. So yes, it is a function according to the vertical line test. In addition, you can look, we have the formula is -2x squared minus 8x minus 3. And if you pick any one x value and plug it in, you're going to get exactly one y value out. So that's another way to see that it is a function. Now the domain is all of the x values that are allowed. So the domain is the set of x values, whereas the range is the set of y values. So on the graph, we can look and see, okay, you can see this kind of, that high point, we call that a vertex for this shape parabolas. And we can see that our x values go to the left, and there are arrows on the end of this graph, which shows that it goes out without bound. And then on the right, we also can go without bound. So our domain is -infinity to infinity. Again, also looking at that graph, we can see that we can plug in any value for x and evaluate it to find out what f of x is or what y is. Now the range is the set of y values. So here we do in fact have a high point. So our graph goes from this high point down. But what is the y value at that high point? That is y equals 5. So now when we use interval notation, we always have to go least to greatest. So on the domain, that's left to right. But on the range, that's now going to be bottom to top. So we'll go from negative infinity to 5. And since this point, negative 2, 5 is actually on the graph, we will include 5 in the range. So we will use the bracket. Next, moving on, we now have 1 equals x squared plus y squared. And we see the graph is a circle. And here, when we test if it is a function, we can use the vertical line test. And we see right away, we fail the vertical line test because we found at least one vertical line that passed through our graph more than once. So this is not a function. And the domain, let's see, how far to the left? Ooh, we do not go without bound. We actually go we stop on both the left and the right. So in this case, we go from negative 1 to 1 on the domain. And we actually also go from negative 1 to 1 on the range. And if you're ever in doubt on the values, if you're supposed to pick 1, negative 1, or 0, you can always write the coordinates. And so on the left, I'll write negative 1, 0, on the right, 1, 0. And since I'm doing the domain, I will only be interested in the x values. Then when I go top and bottom, the top is the point 0, 1. The bottom is the point 0, negative 1. And now since I'm talking about the range, I'll only look at the y values. All right, last but not least on this type. So again, is it a function? Now, if I just have a list of coordinates, one option would be to graph them and use that vertical line test. Another is just to ensure that none of my x values repeat. So here, negative 3, 2, 7, and 3, all of those are unique. So therefore, each x value is paired with exactly one y value. So yes, it is a function. And the domain is just the set of x values. So I just list them: negative 3, 2, 7, and 3. And that should be a comma. I just noticed that. 7, negative 6. Next, for the range, we'll go ahead and just choose those y values. So now we'll just pick those second coordinates and we'll get 0, 4, negative 6, and 4. Now, since 4 occurred twice, we do not need to list it twice because it would just be redundant. So we just list 0, 4, and negative 6. And notice that the 2 was paired with 4 and the 3 was paired with 4. However, that's not a problem because a function just has the requirement that each x value corresponds with exactly one y value. But one y value can, in fact, correspond to 2 different x values. So last but not least, we have one remaining concept, and that is circles. So for circles, the standard form for a circle is x minus h quantity squared plus y minus k quantity squared equals r squared. And that might look complicated in the beginning, but let's hang in there. But what x and y will be our variables. However, the point HK will be the center, and R is the radius. So let's go ahead. I'm going to write out that formula in its entirety. X minus h squared plus y minus k squared equals r squared. So we have our h and k from the center. So we are told that h equals 2 and k equals -4 because the HK is the center. So now let's plug it in. We got x minus 2 squared plus y minus a -4 squared equals 3 squared. And now we just need to simplify. So x minus 2 quantity squared cannot be simplified. However, y minus a -4 is just the same as y plus 4 squared. And 3 squared, 3 times 3 is 9. So this is the standard form of a circle, or I'm sorry, the standard equation of a circle, where the radius is 3 and the center is at 2, -4. Notice the x value of the center appears in with the x in the equation, and the y value of the center ends in with the y in the equation. However, the signs are switched. It's x minus 2 and y plus 4. And that really comes from the fact that the standard equation is x minus h and y minus k. So let's do the next one. And again, this might be a great time to pause and see if you can try this next one on your own. So I'm just writing out the general form. Here we are given our r and hk. So here we have x minus -1 squared plus y minus k, which is 3 squared. And then we get rad 5 squared. So simplifying, we get x plus 1 quantity squared plus y minus 3 quantity squared. And the square and the square root cancel out to give us 5. So our standard equation of the circle with radius rad 5 and center -1, 3 is the quantity x plus 1 squared plus the quantity y minus 3 squared equals 5. Okay, last but not least, we are now going to graph these circles given the equation. So we have x minus 1 quantity squared plus y plus 2 quantity squared equals 4. Again, remembering our formula, x minus h squared plus y minus k squared equals r squared. So now that we have the formula, we need to identify the h and the k. So in A, the x minus 1, we see that h is 1. And then for y plus 2 in that second quantity, we see that the k will have something to do with 2. But if it was just a regular 2, then it would be y minus k or y minus 2. So in order to get it to be plus, the k needs to be -2. So that means the center is at the point 1, -2, hk. Next, we have r squared equals 4. So square root of both sides, Don't forget the plus or minus. However, the radius will be positive 2. So now we need to graph this circle. So I'm going to start and just plot that center point. 1. So I go right 1, down 2, and I'm going to do an open circle. That's the center. And from that center, I'm going to go 2 units in each direction. But it's the easiest to count vertically and horizontally. So I'll go up 2, put a point, back to the center, right 2, put a point, back to the center, down 2, draw the point, back to the center, and left 2. And now I have my circle of radius 2 centered at 1, -2. And that is the graph of this given equation. So let's try B. X plus 3 quantity squared plus y plus 4 quantity squared equals 1. So again, in order to get the x plus 3, h will have to be -3. And that way, when we plug it into the formula, we would have that x minus -3 squared, which gives us the x plus 3 squared. Similarly, we get the y value of our center, k, will be -4. So our center will be at -3, -4. And r squared equals 1. So square rooting both sides, we find that r will be 1. So now our center's at the point -3, -4. And then from that center, we will go up 1, down 1, left 1, and right 1, and draw our circle. Last but not least, we have x squared plus y squared equals 16. Now, we don't have any adding or subtracting in with the x. So h is actually going to be 0. And if we wanted to test that out, we'd go x minus 0 squared just simplifies to x squared. And our y value of our center, k, will also equal 0 since there's no adding or subtracting in with the y. And therefore, our center will actually be at the origin, 0, 0. R squared is 16, so we can do the square root of both sides. Normally, we'd get a plus or minus, but r will be positive 4. The square root of 16 is 4. So now we're centered at the origin, but our radius is 4. So we will go up 4, right 4, down 4, and left 4. And that will give us our circle. So our circle for x squared plus y squared is centered at the origin with radius 4. And now we are ready for the rest of chapter 3.